Hey, all right, here we go again. Chemistry 3202 review. This time we're going to look at Unit 3, Section 3, Lesson 3. This is on the standard molar enthalpies of formation, better known as Smiths. Here we go. All right, Smiths. Here we go. There's the Smurfs. La 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 la. All right, we won't go there. All right, what we're going to look at is standard molar. We already did, I guess. Too late to say that. Standard molar enthalpies of formation, Smiths. And what we're going to look at is calculating enthalpy using these standard values that we're going to get from a table. And if you want to look at the textbook for some more information on this, of course, 642 to 687 there, and a few practice problems. I've got a little sign there that says the easy way or the hard way. Now, knowing full well that most people in general would, given two choices, would choose to go the easy way. Well, what I've shown you is two hard ways, I guess, or not hard, I suppose, but a little more challenging ways to find the enthalpy change of a particular process or chemical reaction. The first way we could find enthalpy change was we would have used calorimetry and measure it in the lab. You know, dissolve some sodium hydroxide in the lab and in a styrofoam cup and figure out the energy absorbed by the water, and then do the first law, and then calculate the delta H equals Q over N like that. Or if we burned the candle under a can of water, we would have to figure out the amount of energy absorbed by the can and the water, and figure out how much energy was given off by the candle X. Very problematic. Every example I just gave you very problematic because it involves experimental error and the assumptions of calorimetry, which would lead to, you know, some discrepancy in our value. We wouldn't really be able to, depending on how good our experiments was, like that candle lab that you guys do, that's not very accurate. So you wouldn't be very confident with that value. The other way we did it, of course, in the last lesson we just did, we talked about Hess's law, where we added up all the different equations until we finally got a target. Well, that's fine as long as you know what your equations are that you have to use. Suppose we give you some kind of chemical and we wanted to calculate some energy value for it, but you have no idea what equations, other steps you're going to have to do, and it take you forever to try and figure out the right ones and all that. So it could be problematic. The only reason it was easy is because we gave you the equations. But once you got an answer, it was very accurate, providing that the equations you used were very accurate. So it was very accurate. What we're going to do here now is something that's easiest of all, and this is going to be using standard values from a table. So let's go have a look at it. Here's the outcomes. Okay, what we're going to look at is we're going to look at standard molar enthalpies of formation. So before we go into that, we have to figure out, well, what is a formation reaction? And we've talked about these a little bit. They show up from time to time. So we look at formation, and we said a formation is simply creating a compound from its elements, so whatever elements are involved. So if I wanted to make water in its standard state, water is a liquid at room temperature and pressure. We'd simply be making this from, say, hydrogen gas, because that's hydrogen, H2, is how it exists at room temperature as a gas. Oxygen exists as O2 as a gas at room temperature. So I'm making water, liquid, from its elements in their standard states at room temperature. And every time I balance these, I always want to balance it for 1 mole of the substance I'm forming. Therefore, we can say it's a molar value. Therefore, standard molar enthalpy of formation. Standard means we're under standard conditions. All right, 100 kilopascals of pressure and 25 degrees Celsius. That's standard conditions. And because we're doing it for 1 mole of the substance form, we say it's a molar value. So therefore, we look at that. Now you can look up this on the table, all right, and if we write it down, we would look at something like this and we would say, okay, this is going to be the notation here. This little circle on top of the enthalpy, the change in enthalpy here, this little circle up top looks like a degree sign. That's going to refer to the fact that this measurement was taken under SATP measurement conditions. The F would tell us what the process is. It's formation. You know, if it was combustion, we say combustion or fusion or solidification or vaporization. In this case, the process is formation, so that's what the little F represents. And this value is very accurate. It's been measured very accurately for us, and it's been placed in the table. And we simply go to the table and get the value, and it works out to be a negative 285.5. And it's kilojoules per mole. Because remember, it's assuming that enthalpy is an extensive property. It depends on how much of the substance is being burned. So if this equation was for 2 moles of water, I'd have to double this value. This is the energy per mole. That's why we would balance it for 1 mole of water. Okay, here's another example. It says we want to figure out what the heat of formation for carbon dioxide is from graphite and oxygen. And we said we did an experiment, and we actually found the energy released by this reaction was 393.5. That could have been done through calorimetry, right? The water would absorb that much energy, and we would have done the calculations to figure out the delta H of this reaction. So what we want to do is simply write the equation for this, and we'll say, all right, where'd it go? The equation for this is simply saying we're going to take carbon dioxide in its standard state. It's a gas at room temperature. We're making it from carbon, which is a solid at room temperature, and oxygen, which is a gas at room temperature. We balance it for 1 mole of carbon dioxide. And the value they gave us here, because it was a release of energy, that means it's going to be a negative value, right? It's exothermic, energy is released. So it's going to be a negative 393.5 kilojoules per mole of carbon dioxide. Okay? These values, if we wanted to check some of these heats of formation, it would be on page 848 of your textbook. All right? On your public exam, they would give you values. The values would be in a table. They would give you the table if you need it, or it would be within the question, and you'd be given that, and you'd have to use those values from within the question. All right? But these are standard values. They're tabulated for us. They're very, very, very accurate. Okay. What we also have to look at here now is we got to look at something called the free elements. Okay, the free elements. Now, a free element is considered to be any element on the periodic table that's in its standard state at SATP. All right, so iron is a solid. Carbon is a solid. Oxygen is a gas at room temperature, standard temperature and pressure. Mercury is a liquid. If I gave you mercury gas, it's not at its standard state, because mercury should be a liquid, not a gas. If mercury is showing up as a gas, that means it has extra energy. It's been excited, right? It's no longer at 25 degrees. At 25 degrees, mercury would be a liquid. All right, so if it's a gas, that means we're at way beyond the temperature of its boiling point. Okay, now for most elements, the element symbol and state of matter is used to represent the free element form. Again, so for instance, if I had, say, the metals like sodium, calcium, aluminum, these guys would all be solids at room temperature. Some of the non-metals, some are solids, some are gases. All right, like the noble gases are going to be gases. The halogens, you got to watch out for bromine and iodine. Bromine is a liquid, iodine is a solid. Fluorine, chlorine, they're going to be gases. Okay, and here's a few exceptions. Phosphorus is a solid, hydrogen gas, nitrogen gas, oxygen, fluorine, chlorine, bromine. The only exception for the metals is going to be mercury. All right, so I'm going to write exception here. Mercury is going to be a liquid at room temperature. If I'm giving you a multiple choice and I say which one is at standard temperature and pressure or which one is going to have an enthalpy of 0, mercury gas would not be 0. It would be excited. Some of these other elements are what's called allotropic, which means they can have more than one form at room temperature. But, for instance, sulfur can have 3 different forms, S, S2, or S8. They've specified that the free element form of sulfur is going to be the form of S. So if I give you S2 or S8, that would be excited forms or higher energy forms, not necessarily excited. That would be referring to the temperature. But the potential energy of these guys would be much higher. They would be a higher energy form than just sulfur. All right. Carbon can have several forms as well, graphite or diamond. and graphite is considered the free element form. So if I give you carbon in the form of diamond, then you're going to assume that the diamond is of a higher potential energy than graphite. Okay? So here we go. The important thing here that we have to note on the bottom is that all free elements in their standard states have enthalpies of formation of 0. Now again, what we mean by free elements is they have to be unbonded and they have to be in their standard state. So these guys are going to be given a delta H value of 0. Now you might be saying, what do you mean given? What do you mean given? How can something be given a 0 value? Doesn't it have energy? Like, we know that fluorine is very chemically reactive. Fluorine wants to gain electrons, very chemically reactive. So why would it have an energy of 0? Well, it doesn't necessarily have an energy of 0. It's not saying that it doesn't have any energy at all. What we're saying is we want to try and come up with some kind of table values here to give some compounds their relative energy. Like, what would it be compared to fluorine? All right, let me give you an example to show you what I'm talking about. The free elements are considered to be somewhat of a reference point. Okay? Even though they have a heat of formation of 0, it doesn't mean to say they don't have any stored energy whatsoever. Because we got to remember that enthalpy is a state function. It depends where you start and where you finish. So what we want to try and do is we want to try and simplify things so that we can have some kind of measurement. And this is what we mean. We're going to assign all the elements from the periodic table as 0 because that's nice and convenient. It's easy to measure and everything is perfect. We know exactly what the state of matter of each element is from the periodic table by simply looking at the periodic table. Because of that, we're saying, all right, what is everything else compared to this free element heat of formation of 0? And let me give you an example. Sea level is a reference point for 0. If you're standing here on the lake shore at sea level or a seashore at sea level, you can climb up to the top of a mountain. And what we're saying is we don't refer to your energy with respect to the highest mountain on Earth, Mount Everest. We don't do that, and we don't go to the center of the Earth. We simply say, well, okay, I'm 2,000 meters above sea level. And that gives you a reference point, and that's easy to visualize because sea level is a nice, convenient location for us. It's easy for us to see where the sea is, how high above the sea are you. Very difficult for us to measure to the center of the Earth. The other thing we can do is we can say, well, we can be above sea level, or we can also be below sea level. Here we are in the sub. If I take a rock here and I'm at sea level and I throw the rock into the water, the rock is going to still have gravitational potential energy, isn't it? The rock is still going to be able to sink to the bottom here. So in this case, we can say that our relative position to sea level is below sea level, and we represent that as a negative. So in terms of energies, enthalpies, we're simply saying this is our convenient measuring point, the elements, very convenient measuring point. Compounds would have energies above the free elements, or they would have energy below the free element. And again, it doesn't mean to say that we have no energy whatsoever. And as I throw this rock in the water, you say that rock has no energy? Watch this. It has lots of energy. It sinks to the bottom. Lots of potential energy. All right, so that's what we're referring to in terms of the free elements being 0. Not that they have no energy, it's that it's just a reference point. And that's a very important point I want to put there, so I'm going to make a footnote here. There we go, great big Sasquatch footnote. There we go. Footnote. All right, they're a reference point only, and that's why they're 0. So, Hess was looking at this and he was saying, well, it's pretty difficult for people to be just trying to figure out, shot in the dark, what equations do I have to use? Let's pick this one, that one, and hope it works out for the best. Not a really good process, is it? Could be there for a while. So what he did, he looked at this and he said, hey, if we assign the heats of formation of 0 for the elements and put everything into relative terms, just like the skiers going down the hill, it doesn't matter how you get there. It's the fact that we went from point A to point B, and the difference between point A and point B we're going to measure that difference and say, okay, that's how much energy was released if I'm going from A to B, or if I was going from B to A, this is how much energy I have to put into the system to get up to point A. So it depends on the direction I'm going to be going in. And that's what Hess is looking at. So he's saying, all right, we can figure out the change in enthalpy for the overall system by simply saying it's the difference of all the products minus the enthalpy of all the reactants. And that's what this symbol is saying here. This is saying all of, the sum of all of reactants, the sum of all of the products. Okay, I know what you're saying. What's with the voice? All right, so we're going to sum all the products and all of the reactants. So what we're looking at is we're saying, okay, let's look at, say, the combustion of methane. Now we could go to the lab and get a tank of methane and put it in a bomb calorimeter and burn it and measure the temperature change and do our calculations to figure out delta H. Very time consuming. Number one, we don't have access to a lab. Number two, we don't have access to the equipment. Number three, how accurate are our results going to be? Because after all, it is an experimental thing that we're doing there. So we want to be a little more accurate than that. We could go away and go get a big book with all types of chemical reactions and their energy values and try and figure out how to get from reactants to products. Time consuming. Hess is saying, forget that. Let's go to our table values on page 848. And what he's saying is I'm going to add up all of these energies, so whatever the energy of carbon dioxide is, plus 2 times the energy of the water. I'm going to add these together, right? And then I'm going to subtract the energy of these guys. And I should be able to get my final energy for the overall reaction. So when I go to my table, lo and behold, I start picking up my values. So I'm saying I need 1 methane. I look at my table, and the heat of formation for methane is negative 74.6. I look at my table for oxygen, but I never ever find it, because we got to remember that oxygen is in its standard state at SAT conditions. That's what this little circle means. We're at room temperature, therefore we can use our table. It's an element. It's going to have an energy of 0 because it's a free element. Perfect. Carbon dioxide, I look this one up on the table. I have 1 of these guys, so 1 times minus 393.5 from the table. Right? These numbers are not magic. They're not coming from thin air. They're coming from the table. And then I look at water. Now water you got to be careful with, because water is found on the table in a couple spots there. It can be water liquid or water gas. So you really have to pay attention to your state of matter here. In this case it's water liquid, and I have 2 moles of water, which means it's going to be 2 times the energy of 1 mole of water, negative 285.8. Okay? What I'm going to do now is I'm simply going to follow down through, and I'm going to do my little calculation here. And I'm going to say, okay, this is going to be the sum of the products. So I'm going to add these guys together, and that goes right there to products. And then I'm going to add these guys together, and that's going to be my reactants. Okay, so everything flips over. We put the values in. So 1 times carbon dioxide, 2 times water, right? Products. 1 times methane, reactants, times 2 times water. All right, we plug our values in that we just found from the tables. Okay, now believe it or not, just like in the last lesson we were doing, negative numbers in calculators, holy cow. Some people have big difficulty with that. You better practice it. So what I'm going to do is I'm going to add these 2 numbers together in brackets. So I'll add these 2 numbers together first, and then I'll add these 2 numbers together, and I'm going to take care of this negative sign now in a second. All right, so take your time and work it out. All right, it works out to be negative 964.6 minus a minus 74.6. Now, if you guys know anything about mathematics at all, you know that a negative and a negative, when you try and multiply a negative by another negative, yep, it becomes a positive. So you change it around. So negative 964.6 plus 74.6, it works out to be a negative 890 kilojoules per mole. Okay? And there we go. Okay, I think I got my significant digits messed up here, don't I? It's 964.6 plus a 74.6. And it works out to be 890, and I need a decimal place there because after all, we're simply doing addition, aren't we? We're not doing any multiplication of measured numbers at all. So in my significant digits here from my table, they're always given in one decimal place, so I'm only doing addition, right? So when we do addition, the final answer should have the same number of decimal places as the least number of decimal places that we're adding together. And all of these guys are plus one digit. Okay, here we go. Let's try another one. This one here is a word problem. It says calculate the enthalpy change, so that's delta H, for the reaction of sulfur dioxide with oxygen gas to form sulfur trioxide. And they always qualify it to say SATP, or they would say standard conditions. That means you can use your table. If it was non-standard conditions, then you're not allowed to use your table. We're not going to go there in this course, for the most part. Okay, so here we go. So we're making sulfur trioxide from sulfur dioxide and oxygen. Make sure you balance it. It's always going to be balanced for 1 mole of the substance you're trying to make. That makes the calculations nice and easy for us. That's why it's called a molar enthalpy. All right, so here we go. We look up our table and we say, all right, don't confuse SO2 with SO3. Very easy to see the difference there, right? This is going to be 1 times this guy plus 1/2 times 0. Oh, 0 because it's a free element. 1 times sulfur trioxide, we get that from the table as well. Okay, now we follow down through here. I'm simply going to skip a step, and I'm simply saying, all right, we can add these two numbers together here, and we can bring this guy down. So when I do my equation, it's saying the delta H of this reaction is products minus reactants. These are my products. These are my reactants. And lo and behold, it makes the calculation a little easier. I don't have to be writing all that information out that I did on the last lesson, or the last problem, sorry. Put it there. Watch this negative sign, negative of a negative. This becomes positive, right? And lo and behold, what do we get? Okay, so this is a positive 296, and it works out to be negative 98.9 kilojoules per mole. Okay, what are they looking for on the public exam if they give you one of these questions? They're looking for you the fact that you've isolated the values from the table or whatever they give to you. And you've also shown them that you know that it depends on the number of moles of the substance. They'd like for you to rewrite this equation here. This equation is given to you, by the way. It's in the table there. You have your table of formulas and constants. That formula is one of the ones given to you. So if you can't remember how these go, check your table. Okay, there we go. Okay, here's another one. This guy's a little more complicated. They're saying calculate the enthalpy change for the reaction of sour gas, and they actually give you the reaction. Here's sour gas, and you're going to react that with some peroxide to produce sulfur trioxide and water. And the equation is balanced, all right? And if it's not balanced, you always want to check to make sure that it is. So in this case, we want to figure out the delta H of this at SATP conditions, hence the circle right here, which means now we can use our tables on page 848. All right. Simply going to look each of these guys up on the table. There you go. And you notice I use my little line down here to separate my products from my reactants. This is going to be 1 times H2S. I find that value from the table. 4 times peroxide. Some people would look at that and think it would be water, but it's not. It's peroxide, H2O2, hydrogen peroxide. And there's going to be 4 times that. 1 times sulfur trioxide, and 5 times water. Again, watch the state here. This is water liquid, not water gas. So 5 times negative 285.8. And again, to make it simple, I'm simply going to add these two numbers together. Now, I'm going to do the math here, and then I'm going to do the math here, just to simplify it. There we go. Okay, so I multiply by 4 and 5 there. Now I'm going to add these two sides together. And now I'm going to do my little Hess's law thing and saying, okay, the heat of the reaction is going to be the sum of the products, which I've already done. Right? I already done the sum of bit right here. I've summed it already. I've added them together. Sum of the products minus the sum of the reactants. And I've already summed the reactants. All right. Okay, I put my values in, watch that negative sign again, and lo and behold, it works out to be 10529, 1 decimal place, because we're doing addition and subtraction. Everything has 1 decimal place. There we go. So that's easy enough, easy marks for the most part. Okay, you should be able to do that. Now you notice that none of these are 0 this time, because none of them are elements. They're all compounds. Right? The only ones that become 0 would be the elements that are in their correct standard state. Okay, here's another one. It says iron ore has reacted with coke in a smelter. Now coke is not like the coke you drink, and it's not cocaine or anything like that. Coke is the industrial name for carbon. All right, so coal and things like that. When they say they coke the furnace, they're actually adding coal to the furnace. They're coking it and heat it up. And in this case, the coke, the carbon, is used not for making heat, but the carbon is being added to this, and it's involved in the chemical reaction where it's actually breaking this down to produce molten iron. Okay, in this case, it's going to be solid iron because we're going to be under standard conditions. And you might say, well, isn't that going to be a lot of heat? Absolutely, but if we were going to actually measure the delta H for this reaction under the heat that the reaction undergoes, that we wouldn't be able to use our values from the table, right? Because we need standard states of these guys. What would their states be at room temperature? So here we go. We look up our values on the table and we say, okay, oh man, look at that. We got carbon in its free element form. That's 0. Even though there's 3 of them, it's still going to be 0. Because it's not saying that carbon doesn't have any energy. We know full well that carbon has lots of energy. If you've ever had a charcoal barbecue, we know we got lots of energy in carbon. But what we're saying is its position on the table, its reference point would be 0 compared to everything else, its position. Here we look up iron 3 oxide on the table, and we got 2 of them. And we've got 4 iron again, but because it's in its standard state, it's 0. You see how we made this nice and simple? And we say then that 3 times carbon dioxide gas, and there we go. So by making it standard states, giving the free element 0, that way we make the calculations nice and easy. So we put our values in, we add these guys up, we add these guys up, so we're summing them. It's products minus reactants. So again, they like to see you write the formula like that, and then of course put your values in, and lo and behold, we get our energy value. Now, I uncovered my notes a little too quick there for you guys. In this particular reaction, they're looking at this and we're saying, well, this is not balanced for 1 of anything. Remember in all the other ones, I said if you want the standard molar enthalpy, then you would have the balancer for the mole of the substance you're looking for. In this case, it's balanced for 3, 2, 4, 3. So I'm looking at this and say, okay, if I wanted to know the molar enthalpy for any one of these, then all I have to do is divide the amount of energy that I get by their number of moles. So for instance, if I wanted to figure out how much energy this reaction was going to give off with respect to the iron, I'm looking at iron and I'm saying, okay, that's for 4 times the amount of iron. So what I'm going to do is say how much energy was released, or absorbed, 467.9. How much energy for 1 mole of iron? Okay, that was for 4 moles of iron. I want it for 1, so I'm going to divide by 4, and therefore I get the molar enthalpy with respect to iron. Get it? If I wanted to do it for iron oxide, then I would have to divide the energy that I just found by 2. So this value down here is no longer a molar enthalpy because it's not specified for 1 mole of anything. Okay, so be careful with that. Okay, here's another one. This one says the heat of combustion of hexane is negative 4361.6. All right, they're giving us that value. They're saying, I'm giving you that. We already know what the heat of reaction is, but this time we want to find a value that's not on the table. We're asking you to get the heat of formation of hexane. So when I look up my tables, I can find this one and this one and this one, but you're not going to find that one on the table. So what we're going to do is we do know the heat of combustion of methane, 4361.6. So what I'm going to do is work it backwards to figure out the heat of formation. So what I'm looking at here is I'm saying, all right, I don't know what this one is. I'm going to call it X. I know that this is an element in its standard state. It's a free element, so it's going to be 0. I can look up carbon dioxide gas from the table. I've got 6 of them. And I can look up water vapor. It's gas, right? So the value is a little smaller. There we go, and there's 7 of them. So what I'm going to do now is I'm going to say when I add this and this and this and subtract them, it should equal that. So what I've done here is I'm going to simplify this and say, okay, let me just extend my line up to separate the reactants from the products. There we go. I'm going to add these guys together. It just so happens that this one ends up being 0, but it may not have been if it was something else. I'm going to add these guys together. It equals X. I'm going to do my math here and here, and then add these guys together because I'm summing them, and I get this value for my products. Okay? Real simple problem here now. Delta H of combustion is the products minus the reactants. I know what the combustion is. They gave it to us right here. I know what my product energy is. I just calculated it. My energy of my reactants, well, it's going to be X plus 0. And so luckily here it works out nice. It's just X. So I'm going to be able to figure out my heat of formation here by doing a simple little mathematics. I'm going to bring this guy over, change the sign, and then I got to watch out for that negative sign. So here we go. I'll take that value over and I change the sign here. I'll do this bit of mathematics and then I have to bring the negative sign over after. And lo and behold, what do we get? Okay, so when I do this right here, it works out to be a negative 308, and this negative has to come over now to turn that to a positive. So there we go. So if I know the heat of reaction and everything else, then I should be able to find the one unknown. All right, nice question for a public exam. Okay, nice question. They want to see the values that you get from your table. They want to see you sum the products and reactants, and then they want to solve this. Okay, and again, now this is going to be kilojoules per mole, so this equation is balanced for 1 mole because it's a molar enthalpy, and that's the substance that the equation is referring to. Okay. Here's another problem, and this is a multi-step problem. This is number 22 on page 688 of your textbook if you want to have a look at it and see how they would state it. But it goes something like this. It's saying how much energy is going to be released when 125 grams of methanol is burned in insufficient oxygen. And we want to be able to figure out the heat of reaction here, or not necessarily the heat of reaction, but we want to figure out how much energy. So we're looking for Q. So in other words, we want to find the amount of heat, Q equals N delta H. The number of moles is going to be easy to find for methanol. The delta H is not given, but armed with our table on page 848 and the assumption that this is going to occur under standard conditions, we should be able to calculate delta H now. So in that question, the only number that was given was the fact that you were combusting 125 grams of methane. Nothing else given, but now we have to use our arsenal here and say, okay, not a problem. We can look these values up on the table. The equation was given to us. Make sure it's balanced. Okay, we can look these values up on the table and we can see that the heat of formation of methanol, not the heat of combustion, the heat of formation, negative 239.2 times 1. Oxygen is 0, nice and convenient. See why we made the element 0? Makes it easy. That's the purpose of it. Carbon dioxide, we look it up, and we got water vapor. So again, 2 times that, we work it out. So what I'm going to do here now is we're going to solve this heat of combustion here. It's the products minus reactants. Now I've got this one done a little bit the long way. You could have easily added these guys together like we did in the last example, but I'm just showing you a different way that some people like to work it out. So it's going to be products minus the reactants. So what they did is they simply rewrote each of these. Then they put their values in. Okay, so the products, CO2, water, 2 times that, and the reactants are on this side. All right, we're going to solve it here now. I like doing it the other way better. It's quicker. All right, we solve this. Watch out for the negative sign. And there you go. Works out to be a negative 637.9. So we've determined that. We now know our delta H. We just don't know the number of moles, so we say that's not a problem. Given the mass, we can easily find the number of moles here. N equals mass over molar mass. And the molar mass of methanol is 1 times carbon, 3 hydrogen, oxygen, well, 4 hydrogens because there's 4 of them, right? Some people forget about that one. But it's 1 carbon, 4 hydrogens, and an oxygen for 32.05. That's the number of moles we have. And then, of course, we can do our calculation. Let me just clean this up a bit. Q equals N delta H. The moles should cross out. And we should be left with a heat term, kilojoules. And there we go. We want 3 significant digits because that's the measured value. We measured 3 significant digits when we measured the mass. These are actual values from the tables. They're only going to have 1 decimal place, but don't worry about it because we're multiplying and dividing here. So the final answer should have the least number of significant digits. So it's going to be 2490. And you might say, well, you know, there's no decimal place, so it's the 2 and the 4 and the 9 are significant, but not the 0. The other way we could do that would say 2.49 times 10 to the 3 kilojoules. There we go. So again, another nice little problem for a public exam where they're getting at the idea of Hess's law, and then they're also getting at the idea of calculating energy from an enthalpy term. So a nice question, probably would be worth 3 marks maybe. You know, 1 for doing this work, 1 for this, 1 for this, and then telling me the number of significant digits and keeping the units. Show all your workings, use all the formulas, right? Show all that. Demonstrate that you know what you're doing so that even if you get the answer wrong down here, they can say, yeah, oh, look at that. Oh, they fooled up under negative sign. Oh, give them 0 on this question? No. I'll give them 2.5 out of 3 because they know what they're doing. They've done this right. They've done this right. The only thing is they got the sign wrong, right? No big deal. So show your workings and everything will work out. Here's one more problem. This is a multi-step problem. That's a calorimetry problem, actually. So in this case, we're saying we want to figure out how much octane, that's gasoline, a form of gasoline, that's going to have to be burned in order to heat 20 liters of ethylene glycol. That's the antifreeze that's in your car engine for coolant. So we're going to take 20 liters, which is a significant amount of antifreeze. That's almost a 5-gallon, 22 liters is a 5-gallon bucket, right? We're going to heat that from -10 to 70 degrees Celsius. And it's telling us the volumetric heat capacity. They give us the heat of formation of octane. Well, I wonder why they gave us that. Why would they give us the heat of formation of octane? I wonder. All right, so let's have a look at this problem. The system is going to be the burning of the gasoline. The surroundings is the engine coolant, the ethylene glycol. Okay, so that's our surroundings. It's not water. It's not a typical type of calorimetry problem. In this case, the surroundings is going to be the ethylene glycol. What do we know about the system? Well, we're trying to find the mass of octane that we have to burn. We don't know the heat of combustion of methane, but we can probably calculate it because as long as we're under standard conditions, then we should be able to calculate the heat of combustion knowing that they gave us the heat of formation of octane. That's why they gave it to us. That should have been your hint to say, oh, yeah. We got to do Hess's law here, right? Okay. What else do we know about octane? Not a whole lot, but we do know that the first law of thermodynamics is going to come into play here, and we're going to say that in order for me to calculate the heat of combustion, delta H is Q over N. So I need to figure out how much energy is going to be released from this burning, and the only way I can do that is figure out how much energy was absorbed by the calorimeter, or in this case, the ethylene glycol. So what do I know about the ethylene glycol? I know the volume, I know the initial temperature, and I know the final temperature. I also know the volumetric heat capacity of the ethylene glycol. Now that's new. What do they mean by volumetric heat capacity? Well, everything up to this point has been a specific heat capacity, which is dependent on the mass. So it would be, 25 joules per gram degrees Celsius. In this case, they're saying it's 3.7 kilojoules per liter degrees Celsius. So for every 1 liter of ethylene glycol, it's going to absorb 3.7 kilojoules. Well, we don't have 1 liter. We've got 20 liters. So we should be able to calculate the energy absorbed by the ethylene glycol. And let's go and do it. So in this case, the energy absorbed by the antifreeze is going to be VC delta T. Not mass this time because our unit is volumetric. So it's going to be VC delta T. We plug our values in here. I'm going to go through this rather quickly. We plug our values in, 20 liters times 3.7 times TF minus TI. So it works out to be a plus 5920. It makes sense because the antifreeze warmed up. It should be a gain of energy. Where did that energy come from? Well, that energy came from the combustion. So Q combustion equals minus Q of the antifreeze. Now that we know what the antifreeze Q is, delta H is Q over N. We want to be able to figure the number of moles here. So mass is going to be N times the molar mass. So we want to be able to figure out the number of moles in order to get the mass. So N is going to be Q over delta H. I know my Q. I still don't know my delta H. So let's figure out what delta H is. Not a problem. We're going to be doing the combustion of octane, C8H18. We write our combustion reaction. They would probably give you that. And it's balanced, of course, for 1 mole of octane. What I do is I look up my values on the table. They gave us this one. That was the whole point of giving us that one, right? So we could calculate the enthalpy here. And we put our values in. Okay, 393.5, which we would not find on the table, but they gave it to us. Oxygen is a pure element. It's going to be 0. Carbon dioxide we look up on the table, 8 of them. Water vapor we look up on the table, there's 9 of them. So we simply add each side together and then do our Hess's law thing on the bottom. So again, it's going to be products minus reactants. A lot of people mess that up. And I know why, because I'll tell you in the next lesson why people mess it up. There we go. So products minus reactants. And lo and behold, we get 4930.7 kilojoules per mole. Okay. So we got our Q, we got our H. We're looking at this and we're saying we could figure out the number of moles. N equals Q over delta H. And if you're not sure where that came from, we know that Q equals N delta H. So if I'm looking for N, I'm simply going to divide both sides by delta H. Delta H crosses out. So N equals Q over delta H. Plug our values in there. The 2 negatives are going to cross out, which makes sense because you got to have a positive number of moles. You got to have some octane. You got to have a negative value for octane. And we got our number of moles here, so now the rest is easy because mass equals N times the molar mass of octane. So 8 times carbon, 18 times hydrogen. And lo and behold, it works out to be 137 grams, which is 0.13 kilograms. 2 significant digits here. Because in this calculation, we're multiplying by 2 significant digits, so my final answer should only have 2, so it should be either 140 grams or 0.14 kilograms. There we go. All right, so multi-step question. Would they show this up on a public exam? Well, if they did, it would be a tough question, but it can show up. What are they doing here? Well, they're testing you on calorimetry, right? First law, calorimetry. They're also testing you on Hess's law. Why not? All right, so 1 mark for this, another mark for this, another mark for this, say, and a mark, that's 4 marks. Why not? It could be a big question, but you know full well if this question shows up, it's going to be worth a lot of marks. 4 questions, 4 marks, you got to do 4 things, at least. Okay, here's one last thing I want to say about enthalpy and its relative position. Generally speaking, if we look at the enthalpy, this is the difference between where we start and where we finish. Let's go back to my little chart here and say Okay, we're going to be like Miley Cyrus. Now that's a bad example. We're going to go up to, we're going to climb the hill. What was the name? I can't remember the name of that song. Okay, we're going to climb the hill. We're going to go up the top here. So suppose we're starting right here. And if I want to go to this point right here, let's call it point B, I have to put this much energy in. Considerable climb. Well, if I want to climb up to point A, I have to go all the way to the top. I have to put more energy in. Generally speaking, the more energy I have to put in, the less likely that I'm going to go there. Like, how many times am I going to climb to the top of that mountain? Look at all the energy I have to put in. I want to go for a walk. Yeah, I'm only going to point B. It's too far to go to point A. So less energy is involved in that transfer, going from sea level to point B, or from any point for that matter. I could be starting at any point. I could be starting just slightly above sea level here. But the answer to this would be, well, if I have to put all that energy in, it's probably not going to occur. That energy barrier is going to be significantly large, that in order for me to get from point C to point A, I have to get that energy from somewhere. I have to absorb that from my environment. The energy has to be provided. So in terms of a stability of a chemical reaction, reaction C to A is probably going to not happen because there's so much energy. It could, right? If we want to provide the energy, it could happen, but probably more likely that CB is going to happen before CA. And that's what we're getting at when we refer to the enthalpies here. We're saying the more negative the heat of reaction, in other words, the more energy we release, the harder it is to get back. So let's go back to our diagram again, and let's say that instead of starting at C, little buddy is going to go up to A, and we're going to say little buddy is going to go down the hill this time. He's going to go from A to B, and sometimes he might want to go from A to C. Now, he knows he's got to get back up to A. Easier to go from B to A than it is to go from C to A. In order to climb from C to A, he has to put a tremendous amount of energy to get back up. So, in terms of stability, once he goes down to C, it's going to be a lot harder to get back. So once products C are formed, they're probably going to be more stable than B because it's easier to get back up to B. You get where I'm coming from? Let me just try and explain this. Here we've got, I'm trying to explain it. Here we got three different chemical reactions. Which one is more stable? In other words, which one is more negative? Which one is harder to reverse? All right. And what we're doing here is we're looking at the signs of their delta H values. And we're saying, okay, this guy is going to release 1100 kilojoules. This guy only releases 142. This one down here only releases 74.6. So to put that into a little bit of perspective, if this guy is going forward, it's going to release all this energy to go forward. In order for this guy to go backwards, all that energy has to be put back in. That's going to be pretty tough. Okay? If we look at the other chemical reactions here, this guy only releases 142. So in order to get back up to the top again, that was 10 times less energy, isn't it, roughly? This guy's 142. This guy's 1,011. 1,000, 1,200. This guy here is about 120, 140. So there's 10 times the amount of energy required to reverse this reaction. This guy is going to be more stable than this one. Once this forms, it ain't going back. The only way it's going back is if it takes a lot of energy. This guy down here, the bottom one, there's only a little tiny bit of energy released here, so this guy is much easier to reverse. So this would be the least stable reaction. This reaction would go forward, but it's just as likely that with a little bit more energy, it could go back. It doesn't take much to push it back. So this is going to be the least stable reactant and product situation. So methane is going to be pretty unstable. And just think about what methane is. it's explosive, right? You can ignite it, boom, it goes up in no time. So it's very unstable. Whereas you look at something like water, well, water really doesn't want to go backwards. Like once you make water, when you combust hydrogen and oxygen to make water, pretty stable, you know. Think about the Earth, 70% water. But if we could pass an electric current through this, we could easily reverse this reaction by providing the energy that would be required. So we could plug this into an electric current, have two electrodes, and we could produce hydrogen and oxygen on the electrode. So we could provide the energy, not a problem. This guy up here is problematic. This is your car. This is your car. It's made of iron. This is the oxygen that's in the air. This is your car rusting. Very difficult to get your car back, isn't it? Once your car has rusted, it's pretty much a done deal. It's pretty stable. Once iron, which is very reactive because it has high energy, it's way up here. Once iron reacts with oxygen, all that energy is going to be released. And now we're in a very low energy state. How likely is that going to be reversed? Very unlikely, because the amount of energy released is so large, it's going to be unlikely that it's going to be reversed. So the more negative the value, the harder it is reversed, therefore it's the most stable. So I'm going to put a little note here. Most stable products have the most negative heat of reaction. And again, that's an important point. I've seen multiple choice show up on the public exam where they simply have 3 heats of combustion and they say which one is the most stable, and that would be the one that's got the largest value. The most unstable or the most reactive is going to be the one with the smallest negative value or the positive value. There we go. Okay, so Hess's law, the easy way. Definitely going to see some of these on multiple choice and long answers on your questions. Throw some of these questions at your tutor. Don't forget, give them a try. There's answers in your book as well. Go get some old public exams. We've got answers on our CDLI webpage. Go into the content, learning content, and go into public exam reviews. We've got 3 or 4 public exams worked out, answers provided, teacher working through them, telling you how to get the answers. Go give them a look. If you can't find it, drop me a line and I'll direct you to it. And there we go. So let's Smith. Anyways, see ya.